Okay, AB Calculus BC, 515, office hours pretest. This is the second part. I'm doing the related rates here, and you will have a few of these on your test. Let's see. So this looks kind of like Lighthouse Rock, maybe, or similar. Ship A leaves harbor at B, headed due south 40 miles per hour. 1/2 hour later, ship C is approaching the harbor at a constant rate of 20 miles per hour from a point 100 miles due east. So this is 100 initially, but then it says, okay, 3 hours after ship A leaves. So this is going to be 3 hours. And it was 1/2 hour later. So this is 3.5 hours. And distance equals rate times time. So if we multiply 3.5 hours times 20 miles an hour, that means it traveled 70 miles and there are 30 miles left. And this one is 40 miles, and this one was, it says 3 hours after ship A leaves the harbor. So that's 120 distance. Let's just double make sure. So it says ship C, 1/2 hour later, ship C is approaching 1/2 hour later. Ship C is approaching. So this would actually be 2.5 hours, right? Because this one's going 3 hours. It was a 1/2 hour later, so it's 2.5 hours. So this should be 50, and that should be 50. Okay, find the distance between the ships. So, I mean, we could give them variables. We call this one A, call this one B, call this one C. So the relationship is A squared plus B squared equals C squared. And A is 120, B is 50. So 12 times 12 is 144, 2 zeros, 25, 2 zeros. So 2,500, that's going to be 961. Take the square root of both sides, plus or minus is going to be 13 with a 0 on it. And go with the positive. So C equals 130. The units, need units, are miles. That's the distance between the ships at that point. No calculus yet. Find the rate at which the distance between the ships is changing. So we're looking for dCdt using my variables. You could use different letters. Make sure whatever letters you use are on the picture. Okay, so we need a relationship, which we've already established and used. Pythagorean theorem. Take the derivative. Now, are any of these values constant? We can plug them in ahead of time, make our derivative easier. Nope, none of them are constant. 2a to the first, dA dt, plus 2b to the first, dB dt, equals 2c to the first, dc dt. And this is what we're looking at. Now, this right here, this is dA dt, and it is positive because A is getting longer. This one right here is dB dt, and it is negative because B is getting shorter. You gotta make sure you get those right. So A is 120, dA dt is positive 40, B is 50, dB dt is negative 20, C is 130, and so we have everything we need. We just got to clean it up and find the answer. So this is 4896 with 2 zeros. This is 100, so 2000, and this is going to be 260. Let's make sure we did all this right. That's good. So 7,600 divided by 260. Take a 10 out. We can divide in half, 13 over 380. So dCdt equals positive 380 over 13 miles per hour. C, find the rate change of theta. So theta is right here. So we're looking for d theta dt at the same time. So we need a relationship. We can do tangent sine, cosine. I'm gonna go tangent. That relies on more of the given information, which is nicer. Do you really want to use dc/dt? I don't. Tangent is opposite over adjacent, b over a, according to mine. Take the derivative, it's going to be secant squared theta, d theta dt, equals, we could do quotient rule, low, d high, minus high, d low, all over, low squared. Secant squared is 1 over cosine squared. Cosine is adjacent over hypotenuse, and adjacent to this angle is the a value. So this is the hypotenuse ends up on top, so that's the c value. So that's 130 over the adjacent side was 120 squared. A is 120, dB dt is negative 20, minus B is 50, dA dt is positive 40. So we can get a negative answer. A is 120 squared. So d theta dt equals, this is going to be negative 2400 minus 2000, 14400 times the reciprocal of this, so 120 times 120, or 130 times 130. I'm going to just leave it like that. That might be easier to work with. So this is going to be negative 4400, right? So we could divide 10 on the top, 10 on the top, bottom, 10 on the top, 10 on the bottom, 100. So we're at negative 44 times 12 times 12, or 14 times 13 times 13. So we can take another 2 out, get 7. So d theta dt, what do we get? 22 times 144, 8, 8, 2, 0, 8, 8, 2, 8, 16 greater than 1, 10 is 11 greater than 1. So we get 3168. I don't know, could I have made this nicer? Let's see. Oh, this is just to be 144. 144. So when, okay, I think I can make this nicer. Took a 2 out. This should be 72. You take another 2 out. This would be 36. Take 6 out. This would be 6. Take another 6 out. This would be 1. So I think we just got 44. 44 on the top and 169 on the bottom. The units are radians per hour. And it came out negative. There you go. Okay. Let's do the next one. Sphere is inscribed in a cube as shown. Both figures are expanding at rates that maintain tangency. When the side of the cube reaches length of 6 inches, the surface area of the cube is increasing at 298 square inches per minute. Volume of the sphere. Find the radius of the sphere. So this is the radius. The sides are 2r. It says when the side of the cube reaches 6 inches, so side equals 6 inches. Well, that's 2r. So that means r equals 3 inches. Find the rate at which the radius is changing. So we're looking for dr dt. So I think we need to use, let's see, probably which radius is changing. So we have surface area of the cube. So surface area of the cube, 1, 2, 3, 4, 5, 6 sides, right? Each side is side squared. We could change it to r, each side is 2r, and then squared. So the surface area equals 24r squared. So then if we take the derivative of the surface area, because they gave it to us, we get 48r dr dt. Perfect. So we can find dr dt. So we have the SAT, the surface area they gave that to us was positive 288. And the radius we just found in part A was 3. So we're going to divide both sides by 48 and 3. 48 and 3. So we take half of this, 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 half of this. 6 goes into 6 times. 6 over 3 is 2. So the answer is 2. dr dt equals 2. Its radius, one-dimensional length, should be inches per minute. C, find the rate of change at which the volume of the region between the sphere and the cube is expanding. So the volume between is going to be the volume of the cube minus the volume of the sphere. And so the volume of the cube is side times side times side cubed. The volume of the sphere is 4/3 pi r cubed. It'd be nice to get this all in terms of one variable, so we'll probably want to put 2r in there, plus we could use dr dt. So the volume we're looking at is 8r cubed minus 4/3 pi r cubed. We're going to take the derivative of that with respect to time implicitly. So we get 24r squared dr dt minus 4 pi r squared dr dt. This is what we're looking for. So let's see what we got. Hopefully we got everything. So the radius is 3. dr dt we just found was 2. So the radius is 3. dr dt is 2. So we're going to clean this up. 9 times 2 is 18 times 24. 32, carry the 3 to 16 is 19, 0, 4, 2, 2, 13, 432. Minus 9 times 4 is 32, 72 pi inches cubed per minute. There we go. All right. Last one, a cone problem, of course. Seems like a pretty common problem. Okay, so this says sand pours into a conical cone, so sand's pouring in. Tank height 4, radius 12 at a constant, so it's 72 cubic feet per minute. That's dVdt, and we should treat it as positive because we're gaining from it. Find the volume of the tank when it's full. So the volume is 1/3 pi r squared h. Now we know we're going to have to use similar triangles at some point. So can we just see if we can use that now? It's going to be r over h equals 12 over 4. R over h equals 12 over 4. So find the formula of the cone's volume in terms of height only. So we're going to have to do that. So r equals 3h. We can do that now or later. It's up to you. 3h squared. So that'd be 9 pi over 3h cubed. So it's going to be 3 pi h cubed. And then so when it's full, the height is 4. So that's 16, 64, 3 times 64 is 192 pi. Units are cubic feet. Need units. So that's full volume. Find the formula for the cone's volume in terms of height. So I just did that. 3 pi h cubed. So you could have waited to do that if you want. C, find the height of the sand in the tank when it is 1/8 full by volume. So 1/8 full by volume is going to be 1/8 of what we already found, 192 pi. Do a little long division if you want. 8 goes in that 2 times, 16, 32. So the answer is 24 pi. That's the volume. And so then we could use our formula 3 pi h squared and set it equal to this 24 pi and figure out what the height is. So this should be cubed actually, right? Okay. So cube root of both sides. Don't do plus or minus. H equals 2 feet. Might need that for something. Find the rate at which the height is changing. So we want to find dh dt. We know dv dt, so let's use the volume equals 3 pi h cubed. Take the derivative with respect to time. dv dt equals 9 pi h squared dh dt. We're trying to find that. So dv dt is positive 72. And we just found the height was 2. So we're going to divide by 36 pi. So dh dt equals 2 over pi. The unit should be one-dimensional height, which is feet, per time is minutes. And that's it. There you go. 3 related rates.